most of you. Okay, good morning. Let us get going again. I was asked at the end of yesterday's lecture to give a good, brief review rather than delving into something new, and I was very reluctant to do that because I thought it's better at this stage. So let me now review what we've done in the first two lectures. In the first one, I was mainly giving you the phenomenology of critical slowing down. So I was writing down all kinds of dynamic scaling relations for relaxation times, for dispersion relations, for correlation functions, response functions, and everything. And that is a little abstract, and if you haven't seen this before, it looks kind of, coming from some wizard's hat. And I told you that is a machinery to actually derive those in general with the normalization group. Of course, these things do show up in the few exactly solvable models we do have, and they certainly show up in simple systems like just diffusion. And then yesterday, I was trying to give you a couple of concrete examples, which I've been writing down in the language of Langevin equations, to get to dynamical scaling near a continuous or second-order phase transition, and for now, near equilibrium. Hopefully, we're going to leave the equilibrium realm later today. And I actually mentioned a little bit of extensions beyond that when I talked about critical aging yesterday. So here's the general setup. We are writing down this Ginzburg-Landau-Wilson free energy functional or Hamiltonian that describes the second-order phase transition. It describes fluctuations, spatial fluctuations in the second-order phase transitions. And then maybe if we couple things to other conserved modes, we need to add a few things for the other conserved modes. They are non-critical, so there is only basically this term with a constant. We don't have to worry about spatial fluctuations specifically for them. We don't need to worry about nonlinear terms and have you. But we need them to couple to the order parameter, otherwise, they just decouple and I can integrate them out entirely and things are boring. And then comes the crucial step of writing down Langevin equations. And the philosophy there was the main argument, we have critical slowing down. So by the very nature of these processes, near a second order phase transition, we are afforded for free by timescale separation. You know that the order parameter and perhaps some conserved modes are going to fluctuate slowly in some sense. So they're kind of generalized hydrodynamic modes. The conserved modes are anyway, but the order parameter will definitely become a kind of hydrodynamic mode as well because of critical slowing down. And everything else, all other dynamic degrees of freedom in the system, we just treat as fast fluctuations, which may have some effect on our system, but it's essentially just a random forcing effect. So we just treat them as noise. And as we don't know anything about these other degrees of freedom and we don't care, we use the minimum information assumption about them, which is we just treat them as Gaussian, for simplicity basically. Okay? So these noise terms are all degrees of freedom that are fluctuating fast on the time scales of this very slow relaxation of the order parameter and then on the time scale of hydrodynamic modes. And so the simplest dynamics that I can then write down for the order parameter is purely relaxational. That's not the full story, and we'll just fix that in a minute. But the simplest one I can write down is assume the system is just going to try and find a local minimum of the Hamiltonian or effective free energy. If it's been perturbed away from that, it's just going to relax back into thermal equilibrium. So it seeks out the h by the s is 0. That's non-zero. I have a relaxation term that drives me back into the minimum. If my order parameter is non-conserved, this just goes with a constant rate that I'm calling d here. If the order parameter is itself conserved, I can't have that. The best I can have is diffusive relaxation. So I need to add, multiply this whole thing with a Laplacian, and I walk through some detail how that comes about. Okay? So that's the crucial difference between non-conserved and conserved fields, order parameter fields in this case. And here I'm just introducing a shorthand notation that allowed me to do things simultaneously for both situations. When I put this I Nabla operator in front here with an A is 0, non-conserved, A is 2, conserved order parameter. Just, helps me in not having to write things down twice. That's really all it's doing. And then there's an Einstein relation by which I can connect the fluctuations of the stochastic forces with this relaxation constant. That ensures that if I look at the corresponding Fokker-Planck equation, and we'll do that later today too, that this system equilibrates to the canonical equilibrium probability distribution. At this point, since I wanted to give you some kind of non-equilibrium perspectives as well, let me say this is actually kind of almost fake. As long as I write down anything here that's a constant, I'm going to be fine. Because you can convince yourself very simply that all I know, if I call some other constant here d tilde, whatever you want to call it, I just need to rescale things. I just need to rescale my fields by that constant, essentially. And I can rescale this thing to be looking like an Einstein relation with thermal equilibrium. Simple exercise. It's actually pointed out in my notes somewhere, which I don't want to go through explicitly, but it's easy to do. All that happens for these models A and B is, if I do rescaling of these fields S, I need to rescale this coupling U accordingly. Okay, so I have an effectively different nonlinearity in my business. I can do these rescalings because all these S's are just dummy variables that I'm integrating over. Once I've done that rescaling to a different U, I will immediately see that for the critical properties that does not matter because U is going to a fixed point on the randomization group flow and doesn't care where I start. So you see that even if this is driven out of equilibrium technically, model A also describes, the model A critical exponents will show up, and so for model B as well. This is why, and it's still surprising people whenever they find it, model A, which was introduced historically as the simplest possible equilibrium critical dynamic system, shows up as a very prominent out of equilibrium dynamic universality class. And it turns out it's actually very difficult to destroy it because you don't have much freedom here if you only have relaxational dynamics. I mean, the only thing you really can do is some long-range correlations in the noise. That gives you something else. You can't do that in thermal equilibrium because Einstein relation prevents that. Out of equilibrium you can. But if you don't put in long-range things, model A is very stable. Okay? Just a side remark and outlook. That's kind of amusing to notice. For model B, I have these Laplacians in front. There I can do something more subtle. I can do a spatially anisotropic violation of the Einstein relation. That drives you elsewhere. Like it takes you to a system that gives you anisotropic scaling. It is a genuine non-equilibrium system. Although, weirdly, you can write this system as an equilibrium system with an effective long-range Hamiltonian that looks like, things look for elastic phase transitions or uniaxial dipolar magnets. I'm just telling you that. It's again kind of worked out in my notes, but I don't have time to go through this in detail. So that was a bit of, an excursion into what happens out of equilibrium. Really, how you can envision this, if this is not 2d kt, but some constant d tilde. D tilde is just d times k effective temperature. You just get any other effective temperature that describes the system. Okay, then we had model C and D. In model C and D, we are coupling a conserved scalar, say energy density, to our order parameter, and that's the lowest order things you can do. I was arguing to you that on the static level it doesn't matter because I can just integrate these bilinear terms out, and all I'm doing is shifting this coupling U. And again, by means of going to a fixed point in universality, that doesn't matter. But it might in dynamics. And so what happens is, these are the situations for G is equal to 0, so model A and B. For model A, the dynamic exponent is a little larger than 2. For model B is exactly 4 minus eta. That's a scaling relation. That's a consequence of the conservation laws. For model C, you really have to distinguish between the cases where the specific heat exponent is positive or negative. The specific heat diverges. In this case, it has a cusp at the transition. It's still non-analytic, but there's no divergence. For n equals 1 Ising case, alpha is positive, and just by writing down dynamic scaling, assuming these fluctuations happen on the same time scale as these fluctuations, which is the last thing I did hectically in 2 minutes yesterday, you see that the dynamic exponent comes out to be 2 plus alpha over nu. So you can fix the dynamic exponent by demanding that both of these slow fields fluctuate on the same time scale. And that turns out to be true in the case n equals 1. Okay? So the coupling to the conserved quantity is actually important and modifies the dynamic exponent to this value. It's still a little larger than 2 and not much, but yeah, that's what happens. If I have more than two order parameter components, alpha is negative, and these things actually decouple. In the sense that the order parameter just obeys model A dynamics, it's non-conserved, and the conserved energy density, if this coupling goes away, just behaves like a diffusive field. So the dynamic exponent is 2, which is a fancy way of saying it's a diffusive field. Okay? And then there's model D. So here we have a conserved order parameter coupling to a conserved scalar density. Now the conserved order parameter already near criticality is fluctuating at much faster timescales. And so there's no way to get these things to obey strong dynamic scaling to be fluctuating on the same timescale. Because the mean field is 4 and 2, and you just can't match that. But there is still one possibility for the scalar case where the order parameter fluctuations feed into the energy fluctuations. So for the order parameter, you always get 4 minus eta for the dynamic exponent, but for this field rho, you get 2 plus alpha over nu of n is 1. But there's no feedback into the order parameter. It's just too fast fluctuating. And for n larger than 2, this coupling goes away entirely. These things completely decouple, and I just get an order parameter independent of the density fluctuations. This is just one example of things that can happen. Once I couple different modes together, here just with purely relaxational dynamics, there is no a priori reason that there needs to be one dynamic critical exponent. Okay? There can be 2. And it can be quite subtle. I just wanted to warn you because sometimes people are a little brazen in assuming you always have one dynamic exponent. You don't need to have that. So this is how far we got. And next I would like to give you one example, first general setup, and then one example where we're going beyond just relaxational dynamics. There's no reason that the order parameter just obeys dynamics that takes relaxation. It's purely dissipative or purely diffusive. There's reversible terms in the dynamics of all kinds of things, such as spins. And we certainly don't want to forget this entirely either. And all this will be featuring very strongly, I'm sure, in Sriram's lectures next week. Okay? Which is a much more complicated system. So we really do need to worry about reversible couplings. But before I get there, and that'll be a little formal initially, are there any questions? So in the kinetics, right? So here, so this would really be, and here? D, yes, you can, right. So you could have long-range correlations in the way things relax, not in equilibrium, but out of equilibrium you can have that. That can matter, depends on what the exponent is, and you can work that out. Likewise, indeed, if you had, colored noise, as long as this is exponential in short range, you can forget it, that scales away. But if I have power law noise correlations, that can matter too, and it again depends on what the exponents are. So there tend to be kind of critical noise. If I do power laws, they tend to be critical power law values. If the kind of power law is decaying too fast, it's going to the short range fixed point behavior. If it's longer, it goes somewhere else. That's the canonical story. And there's something like the critical dimension here that translates into critical value of these power laws, and you have to do double expansion in critical dimension deviation from that power law. Is that what you were asking roughly? So out of equilibrium, you can have all this, and you need to check things. There's no reason out of equilibrium to just write down white noise. People do this, like to do this. It's a great start. It's not the complete story. Okay. All right. And let me try and set up the reversible terms. So we want to start kind of philosophically from some microscopic dynamics. Microscopic dynamics could be Newton's equation, could be Schrödinger's equation. Things are time reversible and invariant. There's no dissipation, nothing like that. Okay, so we're kind of at, in some sense, at 0 temperature. Let me put that in quotation mark because things are a little subtle. And so what you would do if I'm doing the classical language, I would have some observables that live in phase spaces somewhere. And the dynamics of these things classically is given by Poisson brackets with the Hamiltonian. Right, this is Hamiltonian classical mechanics. So I need to kind of figure out the Poisson brackets of the Hamiltonian that will depend on these dynamic variables and as alpha of t. That's fully reversible microscopic dynamics. If I'm talking quantum mechanics, same structure, but what I need to do is, in quantum mechanics, I just need to replace the Poisson brackets by I over h bar and the commutator, where the Hamiltonian becomes this microscopic Hamiltonian becomes an Hamiltonian operator, and these things become the operators that represent the observables. Okay? So let me just keep doing this on the language of Poisson brackets, but you could do this fully quantum mechanically too. So what we're trying to do is we're trying to write down a long wavelength, large time description. So we're trying to look at what's called the hydrodynamic limit. And at this point I need to do a little hand waving. You can make this more explicit in what's called the Moritz-Wanzig formalism, but I'm not going to go through this. We are going to assume that the S alphas we've picked here are all the relevant mesoscopic hydrodynamic variables. Now that's very nicely and easily said, because that is the crux of this problem. If you do this, you solve your problem almost. Okay? It's a very non-trivial step to know what the right hydrodynamic variables are. So let me just say, I just pretend I know that already, but this is a highly non-trivial step that has been done here. Okay, so I assume I know all my slow modes. So these should actually afford me a pretty much complete dynamical description in the hydrodynamic limit. That's what I'm assuming, okay? Either way, yes. I could have a classical system, right? If I talked about momentum, if I do classical hydrodynamics, that would just be classical system. If I'm doing spins, which I'll do, then actually start out the quantum system, play with the commutators, and translate that back to Poisson brackets. Yep, yeah, you're right. So let's start on a quantum level and get back there. But I'll shirk this anyway with the step saying that this is a complete description, because what that means, what I can do is I can keep going here and kind of expand my Hamiltonian formally in these variables. So I'm going to write down kind of a formal expansion where I do dH by ds beta, and then I get Poisson brackets of S beta with S alpha. Okay. I'm expanding, so I need to do a complete sum of things, so that be sum of beta. What I'm also doing is I'm taking this hydrodynamic limit. So in this hydrodynamic limit, really, I need to get to mesoscopic fields. So these aren't really microscopic variables. So what I've kind of tacitly done here is I replace these microscopic variables with mesoscopic densities, which are kind of locally varying. And so that means that really here this is some x prime, this is some x t. Let me just keep that as x here. And then what I need to also do is, like summing here over these discrete indices, I need to sum over the position indices, which is continuous. And so this is a functional derivative that has x prime there. So this is kind of, this is like in quantum mechanics where you expand into a complete set of operators. Here I'm assuming my slow variables afford me with something like that. At this point, I just need these functional derivatives, which show up in the relaxation terms too. And here I need these Poisson brackets. I'm going to abbreviate this as Q alpha beta of x and x prime. If there's a different ordering here, so I call it minus Q alpha beta, because these things are antisymmetric. So Poisson brackets are commutators. And then I'm looking at this again, and I would say, well, this is like the S alpha by dt is some reversible forcing in my dynamics. And I'm just reading off that this term essentially is the reversible forcing. As I said, it's a little formal, but this is how it goes. So with the minus sign picked up from here, this is now an integral d dx prime, some beta, these Poisson brackets alpha beta, xx prime, and then dh alpha by ds beta of x prime. Let me emphasize again, the s's are not necessarily just the order parameter, it's order parameter and any other hydrodynamic modes, other conserved quantities. Okay, so this is the zero temperature story. So let's write down the corresponding Langevin equation, where we try to get to larger than zero temperature, so we have dissipation as well. So what would I do? I would kind of add to this relaxation terms. So I would have these reversible terms as function of my fields, and these might induce all kinds of couplings depending on which of these Poisson brackets vanish or are non-zero. And then I would add relaxation terms. And in the spirit of a Langevin equation, I would add white noise to this. The relaxation terms are of this form over there. So this thing here would be depending on if my field is conserved or not. I would have some relaxation rate. I might have to give it a Laplacian if it's conserved, so A alpha is 2, no Laplacian if A alpha is 0 and things are not conserved. And then this 2 is a functional derivative of the Hamiltonian with respect to my dynamic variables. And I need to specify something about the noise. So let's for now just write down zeta alpha, zeta beta, and call the noise strength lambda, delta of x minus x prime, delta t minus t prime. And let's assume we have diagonalized our system with respect to these noise variables. If it isn't, you just have to do another step. Okay? So this is some type of Langevin equation that will combine what happens microscopically by hand with relaxation terms. If I want to describe thermodynamic equilibrium, I still need to check for equilibrium conditions in this business. So I have to write down the associated Fokker-Planck or Smoluchowski equation, depends on how you want to call it, and check for the conditions for thermal equilibrium. So what's the associated Fokker-Planck equation? So this kind of generalizes motion on your random Brownian motion in an external potential that sits here, and it has these reversible terms here as well. So Fokker-Planck equation always takes the form of a continuity equation, right? So I take change of the probability distribution, and that needs to be balanced by a divergence of a probability current. Let me write down the divergence of probability current in the space of our dynamically variables. It's not a divergence in space X. It's a divergence in the space of dynamically variables. So that means, for example, I need to do functional derivative of whatever this probability current is with respect to my dynamical variables, S of x and t, and set that to 0. So this is, if I forget the x's, this is just my set of discrete dynamical variables, and the sum alpha d by ds alpha is the divergence. Now I have fields, so I have these additional continuous variables. Summing over the continuous variables means the divergence implies a spatial integral. Okay? What's the form of the probability current? Form of that probability current is, well, it's coming from the first moments of increments in the Langevin equation. That gives you the drift term in the Fokker-Planck equation, which I hope relates back to what Sanjib explained last week. So the drift term is just then given by these systematic forces. So the probability current would have the reversible part plus the relaxational part, the systematic terms in the Langevin equation, and all these need to be multiplied with the probability density. That's the drift term. And then you get the diffusive term in the probability current, That comes with the second moment. So this will actually know about the noise correlations if you go back to discussion about the Planck equations. So this comes with 1/2 the noise strength, and now I need the derivative of the probability distribution with respect to dynamic variables, which in our case is a functional derivative. So that's my probability current. So checking for thermal equilibrium means I need to find a stationary probability distribution. We forget thermal equilibrium. We can look for stationarity. What we need for stationarity is the probability density doesn't change in time, and the probability currents don't change in time. So stationarity just means that this generalized divergence here in the space of dynamic variables needs to be 0. That is the general condition for a non-equilibrium steady state. We want to make stronger statements. We would like to have thermal equilibrium. Okay? In thermal equilibrium, we want that the stationary distribution is e to the minus Hamiltonian over kT. So if I look at the stationary limit, so t to infinity or stationary limit, which means dp by dt is 0, so I can forget this bit, I need to somehow get this to 0. But if I look at this form here and do dp by ds, if I do dp by ds in the stationary limit, it pulls me down a minus 1 over kt dh by ds. Minus 1 over kt dh by ds is of this form that I have in the relaxational term. And these things will cancel if this lambda over 2 is equal to kt times that. So I see the relaxational term and this term provided we have the Einstein relation. And then this noise correlation will actually have this kind of differential operator. So we knew that, I'm just recovering that. But to reach thermal equilibrium, we still need stationarity with respect to these reversible couplings. And that we achieve by having divergence-free reversible forcing. So we get that to 0 if we have the integral of d dx, some alpha, and now we need to plug in the d by ds alpha. And we need to plug in f reversible, because that's left. And here we need to plug in the stationary canonical distribution. That's the condition for these reversible forcings to describe, to be compatible with thermal equilibrium. Okay? As I warned you, that's slightly technical, will make a little more sense when we go to concrete examples. Well, let me make a comment. Oftentimes when people discuss are things in equilibrium or not, I give you some dynamical equation of motion of the form of a Langevin equation. There's a lot of discussion of the Einstein relation. As long as I was just discussing before, as long as the form of this is white noise, we get the right operators here, and we don't mess with long-range correlations, I can always rescale this bit. This is not hard to do. I just might have a different effective temperature, but I get an effective equilibrium system once I do this. This second condition on forcings in these nonlinear Langevin equations, reversible terms, is actually usually a lot more constraining. This is the hard one to actually satisfy. And this one tends to be really distinguishing equilibrium situations from situations where you just have non-equilibrium steady states. Or not even steady state. Okay? And we'll see examples for that as we go along tomorrow. So that's the complete kind of abstract theory here, almost. Because if we go back to this condition, this zero temperature form of these reversible couplings does not quite satisfy that, because it only lives at zero temperature. You have to fix that. You can easily fix that by adding a term that turns out to be minus kT dq alpha beta by ds beta. If I add this term, which of course doesn't exist at zero temperature where I was motivating this, if I add this term, this thing actually satisfies that condition, which is a 3 or 4 line calculation that you can easily check. It turns out that often this doesn't actually matter, because often these Poisson brackets are actually independent of the field, so this is kind of automatically zero and you don't need to worry about it. But in principle, this thing is. Actually, your life might be longer in this, but I haven't run into this either. Which is why I was kind of saying this. So this may be a little bit of a fluke. But that's possible, but I haven't seen any real system either where this plays a role. Yeah. Okay, so let's look at one example, and the example I'm going to look at is isotropic ferromagnets. So I'm carefully not erasing my Hamiltonian here, but I carelessly just erased my Langevin equation, but never mind. So for isotropic ferromagnets, I'm going to look at something like the Heisenberg model. So I would have a 3-component order parameter by which I would like to describe the mesoscopic system by a Hamiltonian like that. But I need to get to the reversible terms first. So I need to kind of set back, and as Abhishek was saying, let's write down a microscopic quantum Hamiltonian for this system and see what the commutators are. So I'm going to write down the Heisenberg model with some couplings Jij, quantum mechanical operators, Si dotted into Sj, and then there might be some external field term. Okay, defined on a lattice, say, initially. And let's give them nearest neighbor interactions, but actually doesn't matter. So what are we interested in? We're interested in something like the total magnetization, which is the sum of all these variables, and actually ultimately some expectation value thereof, both quantum mechanically and statistic mechanically. So you do a trace of density matrix times this operator, as we heard in a set of second lectures. Okay, what's the basic commutation relations for these spins? Why they satisfy this commutator algebra. I'm trying to behave and even write down the sum here, not use the sum convention. So if I'm sitting on the same lattice side I would get Sx as y gives me commutator IH bar SC. That's encoded into this asymmetric, fully antisymmetric tensor. If it's Sy Sx, I get minuses. If I'm at different lattice sides, I'm going to consider these dynamical variables independent. So I just give these guys the delta Ij. Okay. So that's the fundamental commutation relation. And with this, you can easily check, but I think I'm going to save myself that pain, because like Sid, if I try to do this on the board, I'm just going to foul up anyway. So I just claim you do this in a 2-minute exercise at home. You do the commutator of the Hamiltonian with this magnetization. So you're summing over lots of ijk's and at some points over spins. And you can easily see that by the fact that this thing is antisymmetric, this commutes. So all components of the total magnetization are conserved in the quantum mechanical sense. Right, so already we know that this order parameter dynamically needs to be a conserved quantity. The best it can do is diffuse a relaxation. That's the input from here. And the other input from here is that we know what the Q alpha betas are. So now I'm doing my mesoscopic limit. I was kind of doing this rather nonchalantly here. This is a highly non-trivial step if you want to go through that formally. Actually, I don't even think you can fully rigorously do this formally. You always have to argue, even in the projector formalism, which is the relevant modes and which aren't. But once you decide on that, you can do formal projection and get to these answers that I gave you here, where I just did a little bit more hand waving. But what is my Poisson bracket? Poisson bracket is really just that commutator. So I've now changed from lattice variables, microscopic, to some kind of mesoscopic fields. I want to get from I over h bar commutator to Poisson bracket, so there's another factor of I. And so that other factor of I gives me a minus sign if I want to insist on that. Actually doesn't matter. And then I get these antisymmetric tensors. This one becomes a field. This Kronecker delta becomes a delta function in continuum. And as I'm doing the continuum limit, this is all dimensionless, so just dimension h bar. As I'm doing the continuum limit here, I'm picking up all kinds of, lattice volumes and stuff. So I'm going to pick up some coupling that I'm just going to call G. Since this is time reversible, the minus sign doesn't actually matter. If you have a plus, which you often see. So with this, we can write down the thus constructed reversible forcing terms for this system. And Sriram and I were just advertising that this term never really contributes, and it doesn't here. There is a non-trivial, so this Poisson bracket actually does depend on the field here, but if I do a functional derivative, I'm just getting a delta, gamma, whatever, and that gets multiplied into these antisymmetric tensors, summed over, goes away by antisymmetry. So the second term doesn't actually matter, and it's just the first term, and so that's all we have. So this gives us a reversible forcing that we will have to add to basically a model B Langevin equation, right? So for our system here, the relaxation term should be conserved, as I said, so that's like model B. And now I need to add these terms, and what I'm adding here is AG, some beta gamma. There's a some beta here. There's a minus sign there, which cancels that minus sign. There's a sign gamma. There's G. There's an epsilon alpha beta gamma. There's gamma of X. And so this is this part. And I need to have the H by D as beta. There was a delta function that kills that X prime and makes it look just like X, as I'm integrating over all space here. Okay, so this doesn't look so hard. And actually, if you stare at that, you see what I'm actually doing as I'm doing the negative cross product of S gamma and dH by ds beta. So if I write the complete Langevin equation in vector form, the reversible term is just the cross product in order parameter space, so the component of dH by ds. And then we have, as I said before, the model B terms. And we get this conserved noise. So this thing in the jargon is called model J, which you notice I want to explain to you E, F, G, and H. Okay. What is that cross product? Now, dH by ds, fortunately I haven't erased this entirely. This is really just a negative local field. So H itself would be the external field, but then there's local field contributions coming from there, if you like. So this is like the Weiss mean field that you play with. So this minus dH by ds is really kind of the effective local field. So what you're seeing here is you get the precession of the magnetization density in the local external field that you have at any space point. So that looks kind of familiar. And it's really the same things that you get in kind of spin precession and quantum mechanics. And then we have diffusive relaxation. So this is spin precession. This is essentially diffusive, but with nonlinear corrections, diffusive relaxation. And we have noise that takes the usual form for conserved quantities. Okay. So we can look at this thing in the high temperature paramagnetic phase. If we look at this thing in a paramagnetic phase, really this S cross dH by ds, if I write this out, will have nonlinear terms. So always S cross at least S, dH by ds starts at S. Actually, let me write it out. So I'm writing out the cross product explicitly again. I get S beta, and now I need to have dH by ds gamma, since I inverted this. So this is going to give me an S gamma. But if I put an S gamma here, I'm having a symmetric product S beta S gamma. I'm contracting it with this antisymmetric tensor. Gone. If I do the nonlinear term here, that's a vector S squared times S gamma, same thing, goes away. So actually the only thing that survives is from the functional derivative here is the Laplacian S, because that one doesn't fully commute. So what happens here is the only thing that survives is Laplacian S gamma. And the other thing that still sits here would be the external field. And then we get model B terms down. Copy those. So that is this equation in full beauty. And what I'd now like to do is linearize this, say, in the disordered phase. Away from the transition, we should get away with the Gaussian approximation and linearization. So I can forget U, and I can actually forget this mode coupling term, because that's quadratic too. It's a nonlinear term. So the linearized theory is just like the linear theory for model B. So it's just the Gaussian model B. So what you see as linear modes in the system are just kind of overdamped, diffusively relaxing excitations. The ones we've discussed yesterday for model B. In this business, they are fancily called paramagnons. And so the dispersion relation is just diffusive. And Q space looks like this. So this just comes from this linearized part, going Fourier space and looking at the poles of the response function, if you like. Okay, so that's the inverse relaxation radius. Okay, so we get overdamped modes. Then you approach the critical point, you get critical slowing down, all kinds of fun stuff happens. And then you can go into the ordered state. If I had, a couple more lectures, I would discuss that, but maybe we do this in one of the tutorials. In the ordered state, this looks very different to model B, because now I need to expand these S fields about the homogeneous magnetization as we were discussing in the tutorial yesterday evening. So there is constant terms here. So we get constants multiplied with these things. So if I linearize, then these spin precession terms will contribute. And what they will actually do is they will generate propagating spin waves of magnon modes. You have to kind of diagonalize in the XY direction by going to circularly polarized modes, but then you get propagating modes with dispersion. The real part of the frequency goes as Q squared, and the damping looks like that. So I'm just telling you that, it's in my notes, you can look at that, it's a straightforward exercise. Okay? But let's look at the critical scaling. So I'm going to show you the power of dynamic scaling, which of course comes with some hidden assumptions that I might make explicit or not. But by dynamic scaling, and we're just staring at the forms of the form of the equation I have here, and assuming that this coupling will survive at criticality, I can actually get the dynamic exponent for this model just by looking at it. So let me try and explain it to you. So as I said, I'm assuming that this coupling G Laplacian S alpha, which is this thing here. Let me not even worry about this. This is just dimensional analysis. So I'm just going to look at G Laplacian S. That gets multiplied with S, and then it's like ds by dt. So G Laplacian S should scale like an inverse time scale. But inverse time scales, we decided, scale like inverse length scales with a power that's given by the dynamic exponent. That's the definition of dynamic exponent. Right, so relaxation time was going like psi to the z, and so this is the typical time scales, goes typical length scales to the z. On the other hand, this is S here, right? Laplacian S. So this Laplacian, if you scale this back, this is really coming from here, it's coming from there. It's really coming from the inverse static susceptibility, which in Q space I know should scale as Q to the 2 minus eta. And so the X should scale in X space, 1 over X, that should scale as X to the, take to this line because that comes directly from here. This should scale as X to the minus 2 plus eta. Write this as X to the minus. So that's the Laplacian here. So Laplacian I've just claimed is really a short form for the full static thermodynamic susceptibility. And then there's this S. The S is like the square root of the correlation function. Correlation function at critical point decays is 1 over X to the t minus 2 plus eta. And that's like an S product. So S should scale as half of that. And so I should have another X scaling, which goes as minus t minus 2 plus eta over 2. So this is coming from static susceptibility. This is coming from the order parameter correlation function. It is slightly hand-waving, but it actually turns out to be correct. And so now I can combine these and read off what Z should be. Okay, so Z will have a dimension dependence, which is d over 2. There's a minus 2, there's a plus 4. So that combines with a denominator of 2 to plus 2. And there's a minus eta over 2 plus eta over 2. It looks like this. So this is my prediction just from dynamic scaling, and actually 0 calculations, but quite inside, of course, of what matters here for the dynamic exponent for isotropic ferromagnets. Of course, if I'm in more than 4 dimensions, I know that eta is 0 because that's a static critical exponent above the critical dimension. And then I get just a d plus 2 over 2. In mean field, I have model B. All the nonlinear couplings go away. And this is going to be larger than this, and therefore faster if D is larger than 6. It's slower than this, and therefore slower if D is less than 6. So this is the right answer if I'm in less than 6 dimensions. That tells me, the dominating answer, that tells me that the critical dimension, the upper critical dimension for this dynamics here is 6. There is, in general, no reason for dynamic critical phenomena to have the same critical dimensions as the statics do. Sometimes that's afforded to you quite nicely, as it was in model C and D, but it's not the case here. So here you get non-trivial dynamic exponents until 6 dimensions. So you kind of get this one until 4, you get this one until 6, and then you get mean field beyond 6. Not that anyone has even ever simulated an isotopic ferromagnet in 7 dimensions. Okay, but that's what would happen. Okay, so here's one example of constructing, slightly formally, I admit, these reversible terms, and then exploiting them and seeing kind of what they do to dispersion relations in the ordered phase, I just said it in words, and to modifying something like dynamically critical exponents. You want to make that actually more rigorous, believe what I just tell you, you have to do some real work, of course. Okay? But this does give you the right answer. Now, let me show you some experimental data that actually confirm this. While this is warming up, are there any questions? No, not J equals 0. Oh, for the equilibrium part, I can just get this directly to 0, so I don't even have to worry about the divergence. Right, because equilibrium really is defined not by just the, just divergence of current 0, but by the absence of current. For the reversible terms, I can't quite do this. So these are experimental data, somehow not published, only on the archive, for a three-dimensional Heisenberg ferromagnet. Maybe that's surprising to those of you who haven't seen this business before. You use the ferromagnets like iron, which you play with and have in your compasses and the like, or cobalt and nickel. Those are a little tricky. So you want to describe something by the Heisenberg mode of localized spins, you need to have ferromagnetic salts. So here's one, cadmium, chromium, sulfide. And they looked at that in 3 dimensions, and they looked at the relaxation scale as function of wave factor, and what they find is a dynamic, nicely power law scaling, and a dynamic exponent is 2.47, so a little less than 5/2, which is what we just predicted. Well, by magic, you can actually explore dynamic scaling in itinerant ferromagnets, such as iron, cobalt, or nickel. This one is an alloy nickel-3 aluminum. So this is really not described by localized spins. This is a fully, as localized spins are too, but this is a fully quantum mechanical system with a Fermi sea of carrying spins and the like, and it's much more subtle to obtain ferromagnetism there. But the symmetries are the same. It's rotational symmetry. The symmetries are the same as in this Lambda Hamiltonian, which originally comes from localized spins. So these guys here looked at the dispersion relation of these paramagnons as they approach TC, and they find that the relaxation rate, which they measure as the width of some Newton scattering peak, very nicely goes with dynamic exponent close to 2.5. So it even works for itinerant paramagnets. This one is dispersion relations of paramagnetic fluctuations directly, and they get 2.47 again. So that's actually really nice. I was very happy to see this. This is not too long ago. This is on my time scales, not on yours. My time scales, that is not too long. Given that this is a very classical system. And then I wanted to add a little bit of a general qualitative discussion that you might find useful, especially if you were experimentalists. So this is a plot that I've stolen from my good friend Erwin Frey and my thesis advisor, Frank Schwabe, from their review, which is a little older, as you plot things in a kind of wave vector temperature plane. So the critical point is at TC and Q is 0. This is the critical point. No one measures quite at the critical point. If you do scattering experiments, it's always in finite wave vector. Because Q equals 0 is forward scattering. In forward scattering, you use a gigantic mess, everything that's not been scattered. So you can't actually do this. Anyhow, so if I'm larger than TC, the basic modes that you would excite are these paramagnons I just discussed, overdamped diffusive relaxed modes. So that's like a dynamical correlation function. At some fixed frequency looks like this. Or as function of frequency for this value looks like that. Then I get these things to really broad because we get subdiffusive behavior at the critical point, right? C is not just 2 anymore, but 2.5 or something. So it's broadened. It's the critical regime. If I'm in the ordered phase, I get propagating modes. So the centers of these peaks are at finite frequencies, that's the propagation frequencies, and the width are the dampings. These two are centered at 0, so 0 is here. I was too lazy to add the axis there. So this is what you see. And then this is the hydrodynamic regime in the disordered state. This is the hydrodynamic regime in the ordered phase. Hydrodynamic regime means small wave vectors on any relevant scales. Okay? Any relevant scales, here is the correlation length. So psi doesn't, even if psi is big, you need to look at Qs that are much less than that. Than 1 over psi. So this is hydrodynamic regimes. That's the critical regime. In the critical regime, you have very large psi ultimately diverges. So here, this product Q psi is actually big. And you get non-trivial scaling functions that make the crossover from this to that, and from here to there. All that kind of non-trivial thing is encoded in these very non-trivial looking scaling functions, which are just kind of brought down. And they're different ones, as you can see, in the ordered phase and in the disordered phase, which I was giving these labels C plus and C minus. So what you do in actually real experiment, you measure at some finite Q that may be close to 0 but not quite 0. And then say you change the temperatures. You go from the hydrodynamic regime here in the disordered phase to some mess. Then you see the critical regime, you see some mess, and then you see the hydrodynamic regime again to the ordered phase. No real sharp transitions because the sharp transition happens down here. So the mess of crossovers is replacing that sharp transition. Of course, you do simulations, you're in the same trouble because you're also not at Q equals 0. That would mean you have an infinite system to play with and none of us can. All right, with this, this concludes what was meant to be my second lecture, but that's fine. So I'm now heading into the third one, which is about generic scale invariance in driven or strongly out of equilibrium systems. But we are going to use some of these philosophies. So I'm going to construct some kind of coarse-grained descriptions for such systems, and then we're going to look at scaling behavior and trying to describe them in terms of scaling exponents. We are now going to be far away from equilibrium. And the one of the simplest systems, anyhow the system I would like to start discussing, is an asymmetric exclusion process, which I think there are quite a few experts in the audience among you that might actually know more than I do about it. But never mind, let me explain this. So this on a discrete microscopic lattice basis is the following system. I take some particles, indicated by black disks here, and they live on lattice sites. They live on lattice sites with exclusion. So all I can have is either no occupation or a single particle on there, and if a particle tries to move onto an occupied site, it just cannot do it. That's the first important ingredient. The next important ingredient is, well, these guys, all they're doing is actually nearest neighbor hopping. But I give them a bias, say, along this transverse direction, this parallel direction, to the right. So they're more likely to hop right than they do left. It's just bias diffusion. If I have no exclusion, all of you can solve this in 5 minutes. Drift diffusion equation, and you just get the overall drift term and diffuse relaxation on top. Easy to do. With the exclusion, it becomes a highly non-trivial problem. And we're going to talk about it. It becomes a highly non-trivial problem, however, only if this is not a finite system, but I'm linking these ends up, or if I do boundary injections and removal. I'm going to forget the boundary injections and removal because that's its own gigantic field, and we could spend 3 lectures easily just talking about that. So what I'm going to do is I'm going to do periodic boundary conditions, most crucially along this drive direction. So I'm going to link these things up to a torus. If I do not do that, and I have no injection or removal of particles, all you would have is a pile up of my particles here and a depletion there. And it's easy to see by writing down corresponding master equations that just gives you a barometric height formula or the discrete version thereof. That's an equilibrium system, or ring. Because all that is the bias would just be essentially like motion of these particles, say, under homogeneous gravity or under homogeneous electric field. And so that gives you this barometric height formula. But once I connect these things, I'm setting up a non-zero particle current. That makes the system to be a non-equilibrium stationary state at long times, and that makes it interesting. It turns out the static properties of at least the one-dimensional asymmetric exclusion process are not that interesting. It's a product measure, but there's very non-trivial time scaling, and we're going to address that. So in one dimension, there is exact solutions for this thing, which are very famous, and you can read up entire books about that. In 2 dimensions, I don't believe such things exist. So we're going to look at this as function of dimension in the continuum description. Okay. Is the model clear? Kind of what I'm trying to write down a continuum description for. By the way, one of the people who invented the continuum description for these things is John Cardy a while ago. So maybe we should swap places at this point. All right, since I'm writing generic scale invariants down, let me explain what that means here. It's really a variant of diffusion. If you think back of what Sid told us in his first lecture, diffusion is of course scale invariant. Satisfies dynamic scaling. In my language, with a dynamic scaling exponent, that's 2. Okay? Now I put exclusion on top. I give these things a bias. It's still some version of diffusion, so we expect still to have some kind of dynamic scaling business. There is no reason for the system here not to obey scale invariance. You see it does. In the language of field theory, it's a massless theory still. It's not a linear theory anymore because the combination of drive and exclusion give us a really important nonlinear term that will modify the scaling exponents below a certain critical dimensions away from the mean field values, which are those of diffusion. So that's the story. We're going to see non-trivial generic scale invariants with non-trivial scaling exponents induced by the combination of nonlinearity, that is exclusion, and non-equilibrium drive. If I don't have the drive and exclusion, it's actually also just diffusive. That is not quite so obvious, but that is true. So I explained the model already. So I have these occupation numbers 0 or 1. Alternatively, I can write down easing variables. This is classical easing variables, which are plus or minus 1/2, by just doing this obvious linear transformation. So if it's empty, I get down spins. If it's occupied, I get up spins. Okay. Then the drive would not be moving things to the right, but it would move something like domain walls along, okay, because it's a continuous flip. As particles move from occupied to empty, they move from spin up to down. So it depends on how you define your domain wall. It either goes this way or goes that way. All right. So I want to have a coarse grained, because that's my philosophy in these lectures. Not everything you could do, but this is what I'm charged to explain here. In a coarse grained description, I'm going to replace these microscopic variables by a coarse grained density. So it would be kind of more a coarse grained magnetization density, which is related to a coarse grained particle density by a similar factor. Maybe it's not 1/2, maybe it's something to do with the lattice size. Let's not worry about that. Okay, and I'm going to play with a half-filled lattice. Because that's easiest, so for the half-filled lattice, I would have the mean density is 1/2, and therefore the mean of this field S is 0. Not really crucial, but yeah, I can do that. I have particle number conservation. I'm not killing my particles. When they leave on this side, they're coming back on this side because I have periodic boundary conditions. Which means this field S or rho or either of them is a conserved field. It needs to satisfy a continuity equation. Okay. I cannot put noise on that level. I can put noise in that describes kind of the stochasticity of the process on the level of these currents again. So this is like the model B. So what I need to specify in kind of the intelligent modeling, I need to specify what these currents are. For those, I need to distinguish between the D-1 dimensional transverse sector, which has no bias in hopping, and the one-dimensional longitudinal sector. So what do I expect in the transverse sector? I told you that even in the presence of exclusion, but absence of drive, I just have diffusion. So I'm just going to write down a noisy diffusion current in the transverse sector. Okay? So that's a fancy word. So what I mean by this is, in the transverse direction, so this vector These are now scalar fields. These are vectors that have components of Cartesian coordinates. So this is the d-1 transverse directions. This would be some diffusion constant, and then times the gradient of our density field. So if I have a gradient in the field, the current would flow such that these gradients are wiped out, homogenized. That's what diffusion does to you. But on this level, I'm now allowed to add noise. And the way that noise is added is, of course, that its mean is 0 and its fluctuations, I and j are now Cartesian coordinates, are given by some noise strength, delta function in x, delta function in t, and Kronecker deltas for the Cartesian directions. Because it doesn't matter what you do in the y and z direction. Okay? This is not an equilibrium system, so there's no reason for me to call this d tilde dkt. Some noise. But I could, as I was arguing before, I have the freedom to rescale my fields and actually make these equal. I will do that later in this transverse sector. Okay? So I can actually kind of formally, by rescaling, recover my Einstein relation in that sector, scaling of the S fields, and set kt to 1 because it gets kind of boring to carry it along. So all linear and just pure diffusion in the transverse sector. What happens in the longitudinal sector? Now here I have to really worry about the drive in combination with the exclusion. And so what is the exclusion bit, right? So we need to go from empty sides to filled sides. So I need to both have an empty and filled side. So there needs to be some term in the drive that goes like rho and 1 minus rho. That's the density of filled sides, density of empty sides. Locally, this is rho of x, and this is rho of x. Well, technically, this might have been the lattice side previous. This is the next lattice side. Once I do the continuum limit, I can't tell that. Both of these are rho of x. Plus gradient corrections, which we're going to ignore. Now, if I look at rho and 1 minus rho, you see rho is just s plus 1/2. 1 minus rho is going to be 1 s minus 1/2. So this is s plus 1/2 and s minus 1/2, minus sign. So this turns out to be 1/4 times 1 minus s squared. The 1/4 is kind of boring. This would be some constant term in the current, but I take the divergence, so I don't need to worry about it. But the divergence in the parallel direction of this s squared term is going to be crucial. All right, so let me write down the longitudinal current, and then we combine these and we get a Langevin type equation that hopefully describes this microscopic system in a coarse-grained continuum manner. So the J parallel of x in t would be this constant, which could also be just the overall current that goes along my loop, right? And it's related to this 1/4, things like that. Then there is a diffusion current with a transverse diffusivity. And because I want to be a little lazy later, instead of writing d parallel, I'll just write c times d, where this d was the transverse one. So I'm just making it different by having a c that isn't 1. So this is s, like there. But here I have to worry about the nonlinear term, which I give a coupling dg, but the important bit, it comes with s squared. So this comes from the exclusion and the drive, and then there is noise here too. Okay? So here I have my two sets of components into this divergence. So this gets multiplied with a del perp, and this one gets multiplied with another del parallel. Put them together, I get my Langevin equation here with dels acting on these vector noises. And minus del eta, I then can call theta and look at the correlations for that, which we've done before. So if I collect all this, what I'm getting is this scalar Langevin equation. which has anisotropic diffusive terms, I'm throwing all this on the right-hand side, so I'm picking up minus sign. This goes with the parallel S squared and noise, where that noise just comes from a combination of these two. And so its mean is still 0. And the correlations come with some strength and conserved noise in the transverse sector, some other strength here. And now I've done that rescaling, so I call the noise strength in transverse sector D, and then we just get our white noise deltas. So that's maybe the effective description for this system. Okay, does that make sense? Of course, there could be higher nonlinearities and the like. By later arguing, if I would, irrelevance and under a randomization group and so on, I can get rid of this. So that's what I have. Now notice that the drive term, for my, if I think of the Ising language here, where I used to have an S2 minus S symmetry, or here you have a particle hole symmetry at half filling, right? The drive term does two things. It's breaking the Ising symmetry. Right? There is the S by dt, all S's. In model A and B, we had S cubed. That was reflecting the Ising symmetry. Here we have S squared. The drive term also breaks spatial reflection symmetry. That's what a drive should be doing. Okay? And they are connected. So this G term breaks the C2 autoparameter symmetry, if you like, and spatial. Very good. So now we can actually go ahead and analyze this a bit. So the first thing we're going to do is just look at the Gaussian correlation. So I throw away the nonlinearity. That's going to be crucial, but let's just look at the correlations first, because those are already interesting. So in this form, this is actually sometimes called just driven diffusive system, or in some acronym jargon, DDS. Let's look at Gaussian correlations. Well, if I look at Gaussian correlations, right, this goes away. This looks like critical model A or diffusion, just with this anisotropies in the game. So in the correlations, what I would have is the noise correlator upstairs and the square of these things downstairs. Just look back in what we did for model A. Very straightforward to do. So I would have a Gaussian correlation function that depends on wave vectors, parallel, perp, and frequency. Upstairs, I get the noise strength in Fourier space, so I would have 2D C tilde Q parallel squared plus Q perpendicular squared. And downstairs, if you don't remember how that worked, we're forgetting this one, I Fourier transforms, throw everything on the left-hand side. It's minus I omega plus D C Q perp squared, parallel squared plus Q perp squared. That's theta, right? And another theta at a different position, and this is all multiplied with S. At a different Q prime and omega prime, this just comes with different Q primes and omega primes. So I just need the expectation values, the Fourier transform, the thetas, and then the average thereof, and then divide by these prefactors to get the correlation function. Fourier transform of these delta functions gives me delta Q plus Q prime, delta omega plus omega prime. And you plug things in and you get the prefactor twice. So So if I looked at this thing in a static limit, static structure factor, so this is t equals 0, what I would need to do is integrate over one of these poles and then take the limit t to 0. Now remember what happens, you basically get the static correlations. The static correlations is this guy divided by that. And then at finite temperature, you would have an e to the minus t divided by the relaxation time, which is this stuff. T equals 0, I don't need to worry about this. And the static structure factor is just that. Again, by direct comparison with what we did earlier for model state. You can infer that. So if you look at that, you see if I approach the q equals 0 point in momentum space, things depend on what direction I'm coming from. There is a angular singularity, there's a phase singularity in momentum space that's induced by the fact that I'm not in an equilibrium system. If I have Einstein relations satisfied throughout, that would mean, after I did one of these rescalings, that C tilde is equal to C. That singularity goes away. Okay? So as long as C tilde to C, we call that W, is not equal to 1, I have a singularity here. Again, it's just a phase singularity. And that indicates that I have a non-equilibrium system. So that's kind of remarkable, right? Because you see that already on this Gaussian level. If this is 1, I really have something that's equivalent to an equilibrium system. And we will see in that case the one-dimensional thing is actually just a Burger's equation, which is as equilibrium as you could get it. But for the Burger's equation, this thing is 1. So what kind of scaling laws would I write down for this? I'm going beyond Gaussian approximation. Well, I have to write down dynamical scaling laws as before, like at a critical point. There is no new, because the correlation length, if you like, effectively is already infinite. Right? So things are already scale invariant. So I need to write down scaling laws. But I need to at least allow for the possibility that things will scale differently in the longitudinal and transverse sectors in space and momentum space, because there's no reason in general for those to scale the same way. The drive may actually induce anisotropic scaling, and it turns out it does. So I need to write down anisotropic scaling. Let me do one version of that, that is Q parallel, Q perp, and omega. And let me define my exponents such that in the transverse sector, I write it like an equilibrium, because the transverse sector really is an equilibrium, if you like. So I'm just doing 1 over Q perp to the 2 minus eta, and that defines what I mean with eta. Okay? Then I get a scaling function that, of course, knows about how frequencies are related to wave vectors. If I do this with Q perp, I call that thing Z. That defines what I mean with Z. In this case, it's actually not something like a Z transverse. But then the anisotropy would be, I need to worry about how Q parallel and Q perp are related to each other. In mean field, they all scale the same way. Everything shows up quadratically. But then it may not be in general true. So let me indicate a deviation from mean field by this exponent delta. That's an anisotropy scaling exponent. So in mean field, in the Gaussian theory, we see this explicitly. I can pull out a Q perp squared. So eta is 0. And Z is 2, which you can see by the omega squared goes as Q to the 4th here. And delta is 0. That's the corresponding mean field scaling exponent. Okay? All right, here's magic. First set of magic is actually there's only one of these non-trivial. And that's by the way I've written them. So if you look back, where is the nonlinearity? The nonlinearity is this term here. Nonlinearity only knows about gradients in the parallel sector. It only knows about Q parallel. In the transverse sector, Q perp, I have a linear theory. So the way I wrote these exponents, therefore, since nonlinearity only shows up in the longitudinal sector, I know that nothing is ever going to change this eta and that z. So this is not a mean field answer. This is the exact answer. The way I define these things. Okay? Let me redefine things so it's a little more interesting. So let me do a Fourier transform into spatial coordinates in time. So I'm going to pick up a scaling function I'm going to call C tilde, which is coming from the Fourier transform of this. So instead of Q parallel over Q perp, I will have X parallel over X perp. And that comes with 1 plus delta. So these are distances. And then instead of omega divided by Q to the Z, I would have T divided by X perp to the Z. Well, I could modify that if I'm so inclined and can make that to an X parallel to a Z parallel. That defines Z parallel. Well, what's the difference there? It was X perp to the Z, but X perp scales like X parallel to the 1 plus delta. So Z parallel here is redefined. That would just be Z divided by 1 plus delta. That's just definition. So we know that's going to be 2 over 1 plus delta. Well, there's a prefactor. I need to change these Q perps. So what do I need to do? So let me write this in time space and define this exponent lambda C. That's the autocorrelation exponent divided by the dynamic exponent, and try to argue what lambda C is. So the 1 over C just comes about as I change from X to T. So I just need to get from here to X's. What I need to do in my Fourier transform, I need to do a frequency integration that picks up an exponent of C somewhere. I need to do a D minus 1 dimensional integration of Q perp that I decided to scale with 1s, and a 1 dimensional integration over Q parallel. That gives me a 1 plus delta. I have to write this in terms of Q perps. Then, as I just said, there is a Z that comes from the frequency integral going back into time, and then there's an overall minus 2 plus eta. If you go through this carefully, this is precisely the values you would find for this. And you see these cancel. C is actually 2, so that cancels. Eta is 0, so that cancels. So this lambda C here is actually just D plus delta. So everything is given in terms of this anisotropy exponent. I have 3 minutes, and these 3 minutes will suffice, even without going much over time today, to fix that exponent exactly. That magic second part. And that works because our system has a new symmetry that is actually not quite there on the microscopic level, but it's there on the continuum level, and that's Galilean invariance. I can basically seat myself somewhere on this overall current, and any reference frame that kind of moves at constant speed along my system is equivalent. Okay? So there's an emergent, and it's emergent because it's a continuum symmetry, which the discrete lattice model, of course, doesn't have. Galilean invariance. And what is that? I can change from X parallel to X parallel prime, which is just the original one. And as I said, go to a moving frame with velocity v. And I'm not changing X perp, and I'm not changing T. So no Lorentz symmetry. just Galilean invariance. And the DG is needed because that's the prefect here. You can easily check that that works. I mean, it just does the job, and I'll do this in context tomorrow. What that means in terms of the fields, though, I need to change the fields. Because under this Galilean transformation, I'm just going to pick up my overall co-moving speed. And so the S prime, this function of all these things primed, is going to be S parallel of X parallel minus DG X perp T, and I need to subtract this overall velocity. And you can check in 2 minutes that that works. Is there a parallel on S? Ooh, there shouldn't be one. Thank you. All right. That fixes, this symmetry fixes delta. Why does it do that? Similar arguments I was just making before on scaling, because you can make this more rigorous by RG means. But what this tells me is that this effective velocity and S scale in the same way. So V scales like S. If I look at this one here, this is a SS correlation function. I'm saying here the scales like T to the minus lambda C over Z, so S itself should scale with half of that exponent. So let's just do this. Let's say this scales as T to the minus lambda C over 2Z. Well, we know what lambda C is, that's just T plus delta. We know what C is, that's 2, so that's just T plus delta over 4. All right, good. On the other hand, of course, if I look inside here or here, my V is also just X parallel over T. Because DG should not actually be scale dependent. That's the tested argument here, and that really is what the RG tells you, that runs to a fixed point. And so this goes like T to the minus 1 from there, and X parallel goes like T to the 1 over Z parallel. Right? But 1 over Z parallel, we just saw, is 1 plus delta over 2. So this is T to the minus 1 plus 1 plus delta over 2. I compare these. The linear equation for delta is function of dimension. And to make that work, we need to set delta equal to 2 minus D over 3. It attains the mean field value, which is 0, at dimension 2. So you read off that the upper critical dimension for the system is 2. I'm plugging this back into here, and I find that, for example, Z parallel is just 2 divided by 1 plus delta, and that comes out to be 6 over 5 minus D. So in 2 dimensions, that's just 2, and we are attaining the mean field value. In 1 dimension, this Z parallel is 3/2. And we're going to use that quite a bit more tomorrow. And the lambda C, of course, I can compute likewise, but we don't need to. All right, 2 minutes. I'm getting better. 4 minutes on Monday, 3 minutes today. Yesterday, 2 minutes. Yes. So the whole thing was running on a D-dimensional lattice. 1 dimension I'm singling out, and D minus 1 is the transverse dimension. There's a reason to call that substrate. We'll see that tomorrow.